So today we're going to talk about AdaCore's CodePeer Advanced Static Analysis tool. This is a complementary tool to our GNAT Pro tool suite, which we discussed in the last webinar. For anyone who hasn't used the CodePeer Static Analysis tool or an equivalent static analysis tool, we're going to cover what an advanced static analysis tool is and how that can help you in your development workflow. If anyone has questions during the webinar, you can use the Q&A box in the WebEx interface. I'll try to get to questions as we're going through the webinar. I might address questions at the end also if we have extra time. So what is CodePeer and what is an advanced static analysis tool? You may be using a basic static analysis tool in your current workflow, where you might be calculating statistics about your code or some basic metrics, like for instance, calculating number of lines of code or cyclomatic complexity. Or you might be using tools that could be checking your code against specific coding standards. These would be considered basic static analysis tools. Another one you might be using would be something called a linter, which is a tool you can use to find basic errors in your code. CodePeer is what we consider an advanced static analysis tool. The general idea is that we're looking to get more information from our code than just simple statistics or basic errors. The way we do that is we look for 3 different types of errors. The first type of error we're looking for are potential runtime errors. For those familiar with Ada, you might be aware that the compiler inserts many checks in the code to check to make sure that things like values going into a variable have the correct range, or you're not dividing by 0, or if you index into an array, is that index valid? These are all things where the compiler is going to insert some checks. Your developers will also insert checks as well. These are going to be things like explicit assertions, pre-post conditions, explicit raises, explicitly raising exceptions. These are all things that are considered runtime errors because we want to make sure our code runs without exception. So what CodePeer will do is that it looks for any point in the code where a potential exception can occur, and it tries to calculate the path, the code path, and the global state that exists to get to that exception. And then it reports that to you. So it will say, let's say we have a function which takes an input variable, and then we use that input variable in the divisor of an expression. CodePeer will say, based on this code, we know that if this input variable has a value of 0, we will have a divide by 0 exception. So, is that possible with our current code here? If it is, what's the probability that it is possible? Or what's the severity of this happening? And we'll get into more about how the probabilities play into the CodePeer results in a few slides. So CodePeer is very good at finding potential runtime errors because the Ada compiler inserts a bunch of checks that the CodePeer tool can use in its analysis. The next type of error that CodePeer is looking for are potential logic errors. These are things that are things like dead code, tests that are always true, never-ending loops, useless assignments. So these are things that CodePeer looks at as a potential logic error. So let's say you have an if-else expression, or if you have an if-else block inside of a subprogram, and CodePeer figures out that the else branch can never be executed because the if statement is always true. What CodePeer is going to report to you is that it says there's a dead block here, the else here will never occur. Another example would be if we have a loop where the exit can never be reached. Now you might be thinking in most applications, we do this on purpose. We have, let's say, our main work loop should be a never-ending loop. So CodePeer will report this to you, and of course you're going to be thinking, well, this is not quite correct because my design says that this is done on purpose. There are ways to tell CodePeer to ignore certain things, and we'll go through that when we talk about the CodePeer results shortly. One of the things that's interesting here about logic errors is this thing that we're calling suspicious implicit precondition. This is a way that CodePeer tries to figure out what logic you're trying to accomplish, and it tries to figure out if that logic has any errors in it. And we'll see an example of this shortly. The third type of thing that CodePeer is going to try to detect are potential race conditions. Now, race conditions are notoriously difficult to compute, especially statically. So when we compute race conditions with CodePeer, what we're really looking for is the usage of protected objects. So for instance, if you have two tasks that are accessing a specific global or a critical section, and that critical section is not within a protected object, CodePeer will flag that as a potential race condition. If you're using Ada83 pre-protected objects, or if you're not using protected objects and you're using operating system mutexing, you can actually tell CodePeer what the lock and unlock calls are using a pragma. So you can kind of train CodePeer to figure out what your application is doing. So it is a little bit flexible depending on what your application looks like. So let's look at some results of CodePeer. This is sort of a digest of what we're going to see in the demo shortly. You can see here that we have some files, stack.adb or tokens.adb, and then we have some line and column information, which is giving us information about where an error is occurring. And then we have some things like medium warning or medium or low. This is CodePeer categorizing messages for us. And it gives us a message after that, and it gives us some information about that message. So let's take the bottom one here, values.adb, line 26, column 12. We have a medium warning. CodePeer is telling us that there's an unused out parameter, and that out parameter is called real_val. So CodePeer detected that we have an out parameter that we're not storing a value in, and it's telling us the name of the out parameter, and it told us the line column information. Now you might be thinking, what's the medium and low thing? What CodePeer does when it actually goes to compute its analysis, it does a primary compilation of your source code. It generates an abstract syntax tree and then walks the abstract syntax tree looking for places in the code where an exception may occur. At each node in the tree, it's going to compute a global state. And then when it finds an exception, it tries to compute the probability that that state can exist based on the program flow. So here we have a medium warning. We have the unused out parameter. And what CodePeer said is that based on the probability of the global state existing at this node, it's a medium probability that this out parameter is unused. So you see here that there's mediums and lows. There's also a high category. So let's look at highs for a moment. I don't have any here listed, but if we have a high finding from CodePeer, CodePeer is telling us that this issue will definitely happen. If we have a medium issue, CodePeer is telling us that this might happen. If we have a low issue, CodePeer is telling us that it's not sure, but it could happen under certain circumstances. So based on this information, when you use CodePeer, you have the ability to figure out what you should focus on, probably highs and maybe some mediums, and what things you can probably ignore until later analysis, probably some mediums and lows. What's interesting about CodePeer is that it doesn't require a compiler to actually do its analysis. In reality, CodePeer has a compiler built into it, and that compiler should be compatible with most code bases. So you don't need to have a code base that was written for, let's say, the GNAT Pro compiler. We actually have a lot of customers who use CodePeer on projects using compilers from other companies, Rational Apex, Green Hills. All of these, they can still use the CodePeer tool to analyze this code. What's nice about that is if you have a legacy code base that was developed under whatever compiler, you don't need to move to a new compiler to get benefit from this tool set. You can still use this tool set on legacy code bases without having to change anything. Let's look at another one of these findings here. Let's look at the difference between medium, a warning and, let's say, a check. So in stack.adb here, line 41, we have a medium warning, whereas on line 93, we have just medium. There's no warning here. What CodePeer is telling us is that when it says warning, a warning means that this is a potential logic issue. When it doesn't give you the word warning, that's a potential runtime issue. So in line 93, that will cause an exception. In line 41, the propagation of this might cause an exception, but this is really a logic issue. The other thing to note here is that we can map findings to what's called CWEs. CWEs stands for Common Weakness Enumeration. This was a catalog of common software issues that was collected by a U.S. security organization. There's about 1,000 findings, and they map numbers to common issues found in code bases. The reason that might be interesting to you is that we're finding that a lot of organizations are starting to look at their code bases for potential security issues. So you might have a security team that might be responsible for developing security reports and risk assessments for your software. Using the CWE analysis, you're able to provide a common language between security professionals and your developers. In most cases, security professionals will not know Ada, and in most cases, your Ada developers might not know security protocol. So let's look at stack.adb line 93. We see after access check that there's 3 numbers in brackets here, 252, 253, and 476. What that means is that this specific issue, access check, which is basically a null pointer dereference, maps to 3 CWEs. So if I were to tell a security professional that I have an access check failure, they're not going to know what that is. But if I say I have CWE 252, 253, and 476, they can go to their database of CWEs, and they understand what that means now. So the CWE mapping gives you an ability to communicate to security professionals with a common language. And you can, of course, turn this mapping on or off depending on if it's useful to you. We'll see some more of these mappings later in the demo. So CodePeer is going, one thing I do want to mention, I did mention how CodePeer does its analysis. It first does a compilation and then walks the abstract syntax tree. The important thing to note here is that CodePeer only analyzes source code. It cannot analyze precompiled binaries. It requires that so if you look at a binary, the Ada compiler generates an abstract syntax tree, that gets passed to the back end of the compiler, which generates machine code, which is your eventual binary. So the transition from an abstract syntax tree to the final binary, you lose a lot of information. So CodePeer requires to do the analysis on the abstract syntax tree, which means that you need to have source code present. The other thing I wanted to mention here is that the CodePeer tool does not come with the GNAT Community Tool Suite. There was a question here in the Q&A, so I just wanted to answer that as we go forward. So some information that CodePeer is going to generate. It's going to generate all those findings that we saw in the last slide. But it's also going to generate a bunch more information that you can use to understand what the tool did and how it interacted with your code. So for instance, a lot of code bases, especially Ada code bases, are going to be integrated with C and C++ or other languages. Or you might have an Ada code base that talks to a precompiled library, for instance. In these cases, the CodePeer tool can only see the Ada code. Anything outside of that boundary, it doesn't understand. So when it sees a language boundary, or it sees calls that it can't see the source code for, so basically you have a spec, but there's no body for that spec, CodePeer is going to say, okay, I don't know where the source code is, so I can't analyze it. However, based on the usage of these calls, of this API, I have an understanding about what this call should and shouldn't do. For instance, let's say I call into a library. That library is precompiled, so CodePeer can't see inside of it. What happens is CodePeer, let's say that call returns an integer, and I use that integer in the divisor of an expression. Let's say since the CodePeer tool can't see inside the library, but it knows that the return from that call is being used in the divisor of an expression, CodePeer can now assume that the return from that library cannot be 0. Otherwise, we get a divide by 0 exception. So CodePeer can insert or can generate a bunch of assumptions based on calls like this. So even though it can't see across a boundary, it can at least give you some information so that you can take that information and verify it against, let's say, your API reference. Other things it might try to generate for you, potential variable initializations or values for various variables and expressions. These are sometimes interesting, especially if you're looking at a chain of calculations where you need to understand the initial values of certain things. But one of the very interesting things that CodePeer can generate are what we call implicit contracts, so pre and post conditions. Those look something like this. We can see here that we have a subprogram called push. And above that subprogram, we have a bunch of comments. These comments are information that was generated by CodePeer. We'll see this in the demo where if you're using CodePeer within the GPS IDE, the GPS IDE can overlay a bunch of this information over the source code. CodePeer does not edit your source code, but with using GPS, it allows you to see things in line. So here we have some contracts that were generated. These are pre and post conditions that we can see here. So let's look at this information to kind of understand what's happening. In this procedure push, we have an input variable, and we're doing some operations. But right at the beginning of the subprogram, we have some defensive checks. This defensive check is saying if some global variable last equals whatever tab tick last is, then raise an overflow. So because CodePeer wants to make sure that you'll never get an exception raised, CodePeer will try to determine how this raise overflow could happen. And we know, based on this check, that if last equals tab tick last, then we're going to get an overflow. So let's look at the information that was generated by CodePeer. We now know that last is a global, and it's being used as an input. It's also being used as an output, because we can see at the bottom there we're modifying it. We can also see that tab is being used as an output. So now we know what globals are being accessed by this subprogram. We can also see that there's a precondition here that says last is in between 2 to 199 or 201. I happen to know that tab tick last equals 200. So if last equals tab tick last, we get an overflow. So CodePeer says a precondition for this subprogram would be last can't equal 200. And we can see that here with the range that last can be in. We can also see that certain things shouldn't be null, certain things should be initialized. So what's interesting about this is we can view this precondition, we can compare that against the specification for this subprogram. We can also look at the post condition here to understand what the subprogram did. For instance, at the bottom of the subprogram, we can see that we're decrementing last. Last equals last minus 1. If we look at the post condition, we can see that this is verified. Last equals last tick old minus 1. What this allows you to do is to view the post condition generated by CodePeer and compare that against the reference for that subprogram to make sure that the implementation matches the specification. So when you're doing analysis with CodePeer, this information is very valuable to look at to understand how the tool interacted with your code. You can view that information and compare that against your documentation for that subprogram. So there's a couple ways you can interact with the tool, and we'll go through a lot more about what the tool actually does when we actually go through the demo here. So for now, let's talk about how you can interact with the tool. We're going to interact with the tool through a GPS client. So GPS is the GNAT Programming Studio. This is AdaCore's IDE. CodePeer is integrated into the IDE, so we're able to trigger the tool, analyze our software, view the results, and interact with the code and the results at the same time via GPS. This is my preferred way to work with the tool, especially when I'm working at it with the tool at my desk. However, we also have a few other options where you can use CodePeer. Like most of our tools, we also have the ability to trigger the tool via command line. This is particularly useful, let's say, if you want to integrate CodePeer into a continuous integration environment. We also have the ability to view the CodePeer results via a web interface. So let's say you have a continuous integration tool that comes by. Once it's completed with its run, it can serve the results of the CodePeer run to your local network, and then your developers can access those results via their web client. They can also access those results via GPS using GPS and CodePeer remote mode. We can also output the CodePeer results in CSV format or raw text format. This is particularly useful if you need to synthesize a report or add things or remove things from the analysis. One thing I wanted to mention here, we have another question here. Someone's asking if CodePeer can check for cross-site scripting, command injection, input validation, SQL-related issues. The answer is no. Those types of issues are application-level security issues. CodePeer is a language-level static analysis tool. So the general idea is that the tool is going to try to find potential software quality issues, which also map to security. To get things like cross-site scripting and SQL injection, you actually need a pattern matching tool, which is a whole different type of static analysis tool. So at the moment, we don't have the ability to check for those types of issues. So when you're using CodePeer, you might be thinking there's a couple ways we can integrate this into our workflow. One of the ways you might use this tool, I mentioned already, when you have a continuous integration tool that comes by, does an analysis of a code base at a given point, and then your developers can come in and triage the results. What's nice about CodePeer is that when you have results, you have the ability to annotate them. So let's say you have a result and you want to say, okay, this is a false positive, or this can't happen based on our design, or this is definitely a bug. Using the CodePeer interface, you have the ability to annotate that finding so that when you run CodePeer in the future, you can see, okay, so this has already been taken care of, or this needs to be fixed. That annotation can be done through GPS, can be done through the web client. It can also be done through source code, and I'll show you those during the demo momentarily. You can also use this tool at your desk. So what's interesting is that the tool has the ability to kind of customize how you interact with it. So one of the ways you do that is by changing the analysis level. So let's look at CodePeer as it analyzes the abstract syntax tree. If I have a very small piece of source code, maybe a couple thousand lines of code, that abstract syntax tree is fairly small and can fit in memory all at once. So CodePeer can do its analysis in what we call one partition. So it can do all the analysis with a single view of the entire abstract syntax tree. But we know that most of your source code is probably much bigger than a few thousand lines of code. We actually have some customers who use CodePeer on a couple million lines of code. In this case, the abstract syntax tree is quite large. So what you need to do is to start partitioning the analysis into sections so that CodePeer can, one, parallelize the analysis and manage the memory it's using. The way you do that is by changing the analysis level. The analysis level goes from 0 to 4. Let's start at 4. 4, the analysis level of 4 keeps the abstract syntax tree in memory at once and does not partition the tree. In cases where you have large, medium to large code bases, we do not recommend this because the CodePeer tool is going to run out of memory and crash. That's not what you want. Let's look at level 0, and then we'll kind of work our way back up to 4. Level 0 actually doesn't even turn on the CodePeer engine. It uses a bunch of what we call lib-adalang checkers, or checkers which can do some syntactic analysis that you're used to from basic linters. This is what you would use if you're at your desk and you want to do a quick check before you commit some code. Do I have any glaring issues? If you move to level 1 kicks on the CodePeer engine, but it only does analysis on a subprogram by subprogram basis. So it does not look at the interaction between subprograms. Again, this is a time you might want to do your analysis. Let's say you're going to commit some code, or you want to make sure you want to look at the quality of your code before a peer review. You could run the analysis at level 1 on, let's say, a few subprograms or a few files, and then take those results and do something with them. If you were to do that on level 4, that might give you too much information for what you're trying to accomplish when you're trying to do basic checks. If you move to level 2 and level 3 will partition the tree only if it runs out of memory. So let's say I do my analysis, I generate the abstract syntax tree, CodePeer looks at that and says, okay, based on the amount of memory I currently am allocated, I will need to partition this into 2, 3, 4 partitions. Level 2 and 3 will handle that partitioning automatically. For most medium-sized code bases, and when we say medium, we probably mean between 250 and 500,000 lines of code, we recommend between levels 2 and 3. if you're analyzing the entire code base. But what's interesting, we have all these recommendations in our documentation, so definitely go check that out. adacore.com/documentation. You'll find the CodePeer User's Guide there. And you can find at in the User's Guide all the recommendations how you should use CodePeer in various workflows. So a lot of this will be covered in there. But what's interesting is that if you have a code base that's extremely complex, or a code base that has a lot of global entity coupling, you'll find that the tool will act differently than it will on, let's say, a very simple code base. Because the tool is so complex and your code is so complex, the tool sort of has a bit of a personality where you'll need to sort of understand how the tool is going to work on your code base and how you can tweak the tool to get the results that you're looking for. And you'll do this by changing that level, the analysis level. I mentioned already that we can map findings to CWEs. This is particularly interesting if you do need to report your findings to a security team. And you have the ability, if you, let's say, have a QA team, to do an analysis in one shot. So you can look at the entire code base, generate an entire report of findings, and then provide some sort of analysis report after that. So the tool should be as flexible as possible so that you can use it in whatever workflow you have in mind. The best workflows that we've seen is when developers can use the tool at their desk to do some basic analysis with level 0 or level 1 to analyze a few files as they're making changes. They then commit that code to version control. And then, once a week, once a month, your continuous integration environment comes by and does a CodePeer analysis at a higher level to try to find potential issues between commits, let's say, or interactions. And then your developers can go and triage those results and make changes appropriately. You might be thinking, well, I have a legacy code base and I don't want to change anything in there, but I want to make some changes to this code base, or I want to add features. What you can do is run CodePeer on the legacy code using what's called baseline mode. This will create a baseline that all your future runs can compare against. So you would say, okay, this is my legacy code, this is my baseline. I'm going to make some changes and then run CodePeer again so that CodePeer can compare my current results with that baseline. What that will do is it will show you what impact your changes had on that legacy code base. That's interesting because you know your code has been flying for 20 years. It's been deployed for a long time. You know that it's fairly stable, so you might not want to change anything in that. This way allows you to figure out what your impact is. You can also have multiple baselines. So what you can do is create a baseline for each delivery and then compare against, let's say, a specific delivery. Again, the tool is as flexible as possible so that it can fit into whatever workflow you need to do. Let's go back to the CWEs, and this is also going to address the question I mentioned earlier. What type of security issues can CodePeer find? This is the complete list of things that CodePeer can potentially find. You'll notice here that I mentioned that CWEs, there's probably about 1,000 of them, and we're only mapping to a handful of them here. The reason for that is that most CWEs do not apply to AdaCore and/or are at an application level. So I mentioned earlier SQL injections. It's difficult to check for that with straight static analysis. You actually need a pattern matching tool. So with using a language level static analysis tool, on Ada, we have the ability to find these issues. We have a booklet on our website, AdaCore.com. If you go to the resources section, there's a booklet there, AdaCore Tools for Software Security. In there, it will explain, it gives you this list of CWEs and it will explain why certain CWEs don't even apply to the Ada language. With the CodePeer tool, you also have access to a few other tools that might aid you in your analysis. I mentioned earlier that you don't need to use you don't need to be using the GNAT compiler. You can be using any other compiler with Ada compiler to use CodePeer. So sometimes when you use CodePeer, it's beneficial to have some other tools around. I already mentioned GPS, and we'll see a demo of GPS shortly. This is an IDE. It's a modern IDE, something like you'd be used to with all the IDEs you currently use. The next tool that's interesting is the GNAT metrics tool. This is a tool that can calculate statistical information about your code. So this would be a basic static analysis tool. The GNAT check tool is another basic static analysis tool. This allows you to check your code against a specific coding standard. What's nice about that is these can sort of fit into your peer review process. You can use CodePeer as an activity before a peer review, but you might also want to check your code against a specific coding standard for a peer review. This kind of will save time in your peer review. So instead of having to check to make sure that developers haven't used certain features of code or have formatted it correctly even, you can use the GNAT check tool to check all that automatically. So now we're going to switch to the demo. I'll show you the CodePeer tool on a fairly small code base. So what we're looking at here is GPS, and I have a basic project loaded in here. On the left here, I have a project file, which is describing a bit about where my sources live and how the tool should interact with my source code. You'll notice that this is a little bit of a complicated bit of information here. All we really need are these 3 lines. So when you start running CodePeer on your code base, the only 3 things you need are you need to tell CodePeer what language you're looking at, and clearly that should be Ada. You need to tell it where your sources live and where the main is. That's all you need to provide it. Once you provide these 3 lines, CodePeer can run on your code. You can edit and generate this project file graphically, so you don't even need to understand what this does. Once we have a project file, we can go up to the CodePeer menu, go to the Analyze window, and that'll bring us to a bunch of options we can select. So you'll notice here, as I mentioned earlier, we have an analysis level, and we have a bunch of settings. For now, I'm going to keep this analysis level as is. We're going to use level 3, which, as I mentioned earlier, is going to try not to partition the source code if it doesn't have to. In this case, it's a fairly small piece of code, so it's probably not going to partition. And we can kind of ignore the rest of these settings for now. We'll come back to them shortly. You'll also notice at the bottom here, we actually have the command line that's going to be run. So what's nice about this is if you are setting up a CI process or you do want to run CodePeer from the command line, you don't need to go through the reference manual to figure out what switches you need. You can open GPS, set up your project, open this window, set it up appropriately, and copy and paste this line into your CI scripts. So for now, let's execute and run our source code, run our analysis. You'll notice here we do a compilation, we generate the abstract syntax tree, and then we do the analysis on the resulting abstract syntax tree. Now we generated a report. So what I was just clicking were a bunch of filters. So let's say I wanted to look for specific issues. So I wanted to say I only want to look for CWE 120 which corresponds to buffer overflow. This is a typical security issue that crops up, where attackers might have the ability to overflow a buffer and access memory they shouldn't. So this one is kind of important for us to understand. If we look at the bottom here, we can see there's an array index check maps to CWE 120. And it requires input.nextWord tick first to be less than or equal to input.nextWord tick last. So what does that mean? Let's look at our source code. So in our code here, we have a case statement where we have a variable word. That corresponds to a string, and we're initializing that with a call to input.nextWord, which we can see here on the left is a function that returns a string. So great. We have a variable word, which is a string, and we initialize it with the return of a function that returns a string. On line 25 here, we have the case word, and we're going to index into the string word with word tick first. So what this means is that we're going to access the first character in the string. But what's interesting here is CodePeer is telling us that there's a potential buffer overflow here. And it's saying input.nextWord, or word tick first, has to be less than word tick last. So this might be a fun exercise for our Ada experts out there. What does this mean? Why does tick first have to be less than or equal to tick last? Well, let's think about a time where tick first equals tick last. How big is an array? So we have an array where the first index is the same as the last index. That would be an array of size 1. So if this is a buffer overflow, and it's saying that first has to be less than or equal to tick last, the overflow would occur when first is greater than last. So what this is telling us is that word, or input.nextWord, can be empty. So if we try to index into the first character of a string, but the string is empty, that's a buffer overflow. And we have no check here to check to make sure that input.nextWord didn't return an empty string. So what we would want to do here is before we access word tick first, we'd want to have an if statement that says if word tick length equals 0, do something else. That way we wouldn't have a potential buffer overflow. Let's look at another finding here. We'll go back to the CodePeer report, and I'll turn back on the rest of these findings here. You'll notice here that we talked earlier about the different categorization of messages. We have highs, mediums, and lows. As you can see here, we don't have any highs, which means that there probably isn't anything that will, any exception that will always occur. There are exceptions that will probably occur based on certain inputs. Let's look at here. This is the subprogram we saw earlier in the presentation. We have this procedure push. Now we know this is in a package called stack.adb. So now we know that this is a stacked data structure. The push operation on a stacked data structure should add information to the underlying array. So based on that, we know what push should do. So let's look at our preconditions here and our postconditions. Well, actually, first we can look at the issue. Suspicious precondition for last, not a contiguous range of values. So it's saying the precondition that CodePeer generated is suspicious. Let's look at that precondition. That precondition is here. Last is 2 to 199 or 201. And CodePeer is telling us that the gap in the range here is a little bit odd. So let's look at our procedure here to figure out why. We already know that last can't be equal to 200. Otherwise, we get an overflow. And we can confirm that. So if we go to last is a natural, and it's starting at tab tick first minus 1. Tab, right above it here, is an array of 1 to size. And size is equal to 200. So we know that if last equals 200, then we have an overflow. So that makes sense with our precondition. But what's interesting here is we see that last has to start at the value of 2. And we can see here that the initialization of last is tab tick first minus 1, which is 0. So if we were to push a value onto the stack, last would equal 0, which means we would have a precondition failure. So something is wrong here. And we can kind of figure it out when we look down at the end of the subprogram here. If we look at the push operation, push should take a value, increment the index of the stack, and then put that value at that new index. So let's go through the exercise of talking that out. Last is equal to tab tick first minus 1, or 0. When we go to push a value onto the stack, we'd want to increment last to 1 and then put that value in tab index 1. That would put the value at the first index of the array. If we look at our procedure here, you might notice this line. Someone probably copied and pasted something incorrectly here and used the wrong sign. So what CodePeer told us is that you have a logic error. We don't know what it is because we don't know what a stack is. We don't know what push is because we haven't provided that information. But something is wrong. We're going to give you as much information as physically possible in the preconditions and postconditions here so that you can understand what might be incorrect. And from that, we've determined that this sign right here is incorrect. It should be a plus. We should be incrementing last instead of decrementing last. So what's nice about CodePeer is that it is extremely intelligent, but will only work on the information you give it. So with Ada, luckily, the language is very syntactically rich. So CodePeer has the ability to work on a lot more information than it would, let's say, on other languages. The compiler inserts a lot of checks that CodePeer can use. However, things like data structures and logic, CodePeer only can figure out what's at the language level. Unless you start providing, let's say, Ada 2012 contracts, where you start to describe the functionality of a subprogram using a specification, if you have those types of things, then you have the ability to tell CodePeer more information. If you don't have those things where you're using, let's say, Ada 95 or even Ada 83, then CodePeer will work on as much information as you can give it. And as we can see here, we have a little bit of a cryptic message from CodePeer, but we were still able to figure out, based on the information that CodePeer provided, what could potentially be wrong. Let's go back to the CodePeer report. You'll notice here that there's a message review status. Everything is considered uncategorized until you categorize it. So as you can see, we can take things and make them not a bug, or false positive, or a bug. Let's actually see how we can do that. Let's go back to our array index check fail here that we looked at earlier. And let's say we know that by design, this buffer overflow cannot happen. What I can do is I can grab this little review message icon right here. That's going to open up a window where I can categorize this. Or I can say this is intentional, it's approved by me, and this is intentional. What I've just done is I've now triaged that result and categorized it. If I go back to the CodePeer report, we'll notice that one of the mediums disappeared. I'll go to intentional, we'll see that show up. And we have our finding here. If I click on the review message again, we can see that that has now been inserted into the database. There's another way we can go about this. And one of the issues with the methodology I just showed you is that what we're actually doing is editing a database. That database lives on the machine. So if you have a system where you're using a continuous integration environment, your developers can access, let's say, a common database. But that database needs to be persistent. So let's say we can't have a persistent database, but we still want to annotate findings. What I can do is I can do something like this. Oops, excuse my terrible typing here. I apologize. I've just done effectively the same thing, where I've now told CodePeer that the next line underneath pragma annotate should be categorized as intentional with the message this is done intentionally. So a couple questions here that I can address that are in the Q&A box. And if anyone has any questions, definitely go to the Q&A box and ask them. We have a few minutes here to address some questions. So the first question I wanted to address, is the output file for CodePeer compatible with other tools? One of the examples was Vulnerator. So I'm not sure what that tool is, but I assume it's a security aggregator. We don't partner directly with that tool. However, we do have the tool can output CSVs. So it's possible that you can take the CSV output of CodePeer and manipulate it to get it into another tool. We do have customers that do that fairly regularly. For instance, that we do know that there are customers that have proprietary security tracking systems and things like that, or bug trackers, and so they use the CSV output to take that information and drop that into their current system. Next question here, is there a trial version available? So the answer is yes. So if you do want to take a look at this tool and learn more about it, you can contact us, sales@adacore.com, or you can go to the AdaCore website and go to the Contact Us box and tell us what your project's about, or what you're looking at. Tell us, that you saw CodePeer through this webinar, and one of our account managers will get back to you, get more information about your project, and we can provide evaluations of the tool. The next question here, can CodePeer analyze Windows source code from 64-bit Linux? This is a good question, or 32-bit Linux from 64. The answer is yes. So because CodePeer is agnostic to what the code was intended for, CodePeer can analyze anything that's valid Ada code. It doesn't actually compile it to the final target, so it doesn't really matter. So for instance, we have customers who are using CodePeer on systems that are compiled for Solaris, but they're using CodePeer on Windows or using CodePeer on Linux. So again, CodePeer doesn't care because it's only looking at the source code. What's interesting about CodePeer is because it doesn't care about the source code, it only requires that it's valid Ada, and that valid Ada can be Ada 83, 95, 05, 20, or 2012, or even 2020 if you're using some of those features. So as long as it's valid Ada code, CodePeer can analyze it. All you need to do, if you don't already have a project file like we saw here, is to set one of those up. And all you need, again, are these 3 lines. We have some tools which can help you automate generating project files so that you don't need to create your own. So for instance, with GPS, you can create a project file through the user interface. And we have some wizards and some command line tools that can kind of figure out where your source code is and generate a project file from that. If anyone has any more questions, definitely ask in the QA box here. A couple other interesting things about CodePeer. Again, the tool is standalone. So if you have an application, even if you have a partial source code, let's say you have a library that you need to analyze and that library doesn't have a main, that's perfectly fine. All you need, again, is a project file that's set up correctly, and the tool can analyze it. The only issue is when there are missing specifications. So this is a case where you have, let's say, a compiler where that doesn't, and you don't provide a compiler that's not GNAT Pro, and you don't provide CodePeer the specifications for the runtime. That would be a case where you might have a problem. But we have the ability to generate some runtimes for some common, or some runtime equivalents for some common compilers out there. So what we can do in that case is we can analyze the source code up till it hits the runtime, and we can't analyze the interaction with the runtime. If you'll notice here in the CodePeer report, you can see that we actually, because I'm using the GNAT Pro compiler, it actually analyzed the runtime and actually analyzed the interaction with the runtime. If you're not using the GNAT Pro compiler, it will not be able to analyze the runtime, but it can analyze the boundary of that runtime. The other interesting thing about the tool, and we have had a couple cases of this where people are working on systems that are not 32 or 64-bit. They're doing analysis on 16-bit, for instance. And the tool can handle that. What you would do is you would provide a file to the CodePeer tool that describes the size of various variables and the size of, let's say, the address space and things like that. And then from that, CodePeer can adjust its analysis to take into account the modified size. So let's say if you want to do a 16 or even an 8-bit code base, you can use CodePeer to analyze that. So after the webinar today, you should receive an email with a recording of this webinar. And if you have any questions, you can contact us at sales@adacore.com, or you can go on our website, adacore.com, and find the Contact Us link there. You can also find documentation about CodePeer, and you can find resources about CodePeer, about security, about GNAT Pro, and all of our tools available at AdaCore. If anyone has any questions, again, send it to sales@adacore.com, and we'll be happy to get back to you. Thank you all for attending, and we'll see you at our next webinar. Thank you.